No. All right, welcome back to the drive-thru, sponsored by the deli. Hungry? Stop by the deli and get yourself a delicious grilled cheese sandwich on sourdough with sharp-aged Wisconsin shredded white cheddar. That's a lot of adjectives, but it takes that many adjectives to make such a great sandwich. I think it is. Okay, we're good to go. This is 14.1, and I'm going to do the best job that I can, but hopefully, if this is the year 2017, someone is watching this video and telling me you need to make a new one, because I will do better at this next year than I'm going to do this year, okay? So, this is an introduction to vector fields. I have no idea how long we're going to spend on this, but today, what we want to be able to do when we're done with today is understand what a vector field is, and understand the best strategy in sketching vectors in vector fields so we have some sort of an idea of what is going on, okay? So, by definition, a vector field is a function where you input independent variables x and y, and what you get out of that is a vector. Okay? So that would be a two-dimensional vector field. Here you've got three independent variables. I think the book uses P. Okay, and that would be a three-dimensional vector field. Just keep in mind that in our class, we often write that like this. Whoops, nope. Like this. All right, in vector notation instead of component notation. All right. Oh, it is a P. Thank you. Okay, so a couple things. Velocity fields. Think about a wheel spinning around, okay? How about an old-fashioned, what do they call those things? Carriage wheel with spokes, wooden spokes. If you were a bug on that spoke, the further you are away from the center of that wheel, the faster you're traveling. Could you imagine that? Your rotational velocity increases as you get, is that the wrong way to use that word? Your velocity increases as the radius increases. Now, actual application of that is golf. Okay, which club hits the ball the furthest? Which golf club hits the ball the furthest? The driver does. Most people think it's because of the loft on the club and the size of the club, and it does have something to do with that, but it is mostly because which club in your bag is the longest? The driver is. So when you swing it, that club head speed is significantly faster than a shorter club, and that's why it hits the ball further. Now you can also think about it is that's also why the driver is the hardest to control, because any little change in angle in your hands is going to be magnified by a further distance away, and with more speed, it's going to create a greater range of error. So like most things, it's higher risk and higher reward, okay? All right, let's just try to practice one. Okay, so for now, I'd rather you not follow along in the book, because I think there will be a momentary aha or mind-blown moment when we do this, okay? So look, this right here is a two-dimensional vector field. Do you recognize it from the last slide? It certainly seems like it's going to be linear or planar. That's a really simple vector field, don't you agree? Okay, so what it wants us to do is when we're plotting these vectors, it wants us to plot vectors of equal magnitude. If you plot vectors of equal magnitude, If you plot vectors of equal magnitude, you will have your best opportunity to learn what's going on in this vector field. Okay? Keep in mind, how many vectors are in this vector field? Infinite. So if we plotted all of them, we wouldn't learn anything. They would all overlap with each other, and we would never have any idea of what was going on. But if we just plotted one, we would have no idea what was going on. So there is a right amount of vectors to plot, and that's what we're trying to help you with right here. Okay? So what this pink hint means is we want that. Okay? So how do we find the magnitude of a vector? That's right. So C is going to be the square root in this problem of negative y squared plus x squared, right? We dropped our i's and j's because we're talking magnitude. So then what you get is c squared equals, well, you get y squared plus x squared. I'm going to switch them for us. And so now we've learned that if we want to plot vectors of equal magnitude, we should plot them along which shape? Circle. If you're great at this class, what you're going to quickly understand is that this is so closely related to our gradient stuff. We're learning it in a backwards order. Okay? If that doesn't make any sense to you, then don't worry about it. So, let's start by letting c equal 1. So where along a circle can we pick points where c equals 1? Let's just pick the easiest ones possible for today. So 0, 1, 1, 0, negative 1, 0, and 0, negative 1. Okay? So what I'm going to do is I'm going to have to toggle between, because I want to put this on a nice big graph. Okay, we're going to let each space here equal a half of a unit. So that's a 4. And that's a 4. Okay, so at the point, let's rewrite our function. F of x comma y is negative yi plus xj. Is that right? Is that what we had? So what do you get at the point 0, 1? What's our vector? I disagree. Negative 1, 0. Right? You're taking any point you wish, an independent variable. You can pick whatever point you want. You plug it into our function, and what's it spit out? It spits out a vector. So at this point, our vector is, oh, let's not use black. Our vector is that, right? And what is it at, what was our next point that we decided to do? So at 1, 0, what was it? What do we get? 0, 1? Okay. So at 1, 0, we have this, right? Right? Okay, and then at negative 1, 0, what do we get? 0, negative 1, I agree. At negative 1, 0, we get this. So our last one to do is this point right here, 0, negative 1. And what do we get for that? 1, 0. And that's good, because I hope that's what you guys all expected to get. So far, so good? Okay. Now, let's let C equal 2. Okay? Hold on, if I go back to this, what I want you to understand that's important, did you see that all of these had a magnitude of what? They better, right? Because we set them equal to 1. So now if we let c equals 2, what will our points be? 0, 2, 2, 0, negative 2, 0, and 0, negative 2, right? Okay, so let's continue with those. And we should be able to look at our little map and be able to get these really quick. So what's this one going to be? Negative 2, 0. Let's just keep doing our math. This one? 0, 2. This one? 0, negative 2. This one? 2, 0. Okay, I'll plot these in blue. So here, it's now that. Here is that. That. And that, right? And let's just do one more. How about, let's see, radical 2, radical 2 should work, right? Yeah, because c equals 2, so c squared would be 4, and radical 2 plus radical 2 squared is, radical 2 squared plus radical 2 squared is 4. So, let's do another point here. Radical 2, radical 2. What's your vector? Negative radical 2, positive radical 2. So that's going to be, let's see, radical 2.
So it's right about the third x.
Yeah, I got you. Somewhere around here. And it's going to be this. Same magnitude. You feel it? So maybe what you can see is that inside there, okay, and what this is our velocity field on a circle. It's exactly what we described in the golf club example, or the spoked wheel example. Do you understand that? The further away the particle is from the center of the wheel, the faster it's moving at any given time. You understand now?
So is each circle a vector field?
Each circle is a level curve. The entire thing is a vector field. Okay?
So would the entire xy plane be a vector field?
Yes. The vector field is the sketch of the vectors that we choose. Keeping in mind, there are infinitely many vectors here, and if I drew them all, it would be a colored-in piece of paper. Okay? So far, so good? All we're trying to do today is be able to sketch these, and then be able to read page 1009 and understand what it means. Okay? All right, example 2. Let me pause there. Okay. So we're just going to go through this problem blindly and do the same process as we did the last time, and then try to figure out what the heck we just learned from it, okay? So we want the magnitude of f to be constant. So we want to figure out what types of, where we should plot points so we have vectors that are equal magnitudes. So that means c is equal to the square root of 4x squared plus y squared, right? So then you get 4x squared, 4x squared plus y squared equals c squared. We're going to leave it like that, but just remember that would be 4x squared over c squared plus y squared over c squared equals 1. When you simplify this, which c value is going to be bigger on the bottom? I know they both look the same, but this one has a 4 on the top. So the y will have a bigger c value on the bottom. So what Where is this ellipse going to be pulled? In the y direction. It's going to be stretched vertically. Okay? So, if we let c equals 1, what are some points? We've got to pick the easiest points for x and y to let c equal to 1. Well, here's two easy ones. 0 comma something and 0 comma negative something. What would that be? 1 and negative 1. And then what would we do?
1/2 0, negative 1/2 0.
Excellent. Okay? What's our vector here? What's our vector here? Here? That's good. That's good. We want all these to have the same magnitude, so we're doing it right. And then I'm assuming negative 1 comma 0, correct? So let's plot them. Same thing, we're going to have all these be a unit. Okay, so at the point 0, 1, we get the vector 0, 1. At the point 1, 0, we get the vector, at the point 1/2 0, we get that same vector, right? There's this one. Yep. No, 1/2 comma 0, right? Yeah, that's a half. Okay? So what I'll do in black is just dot out the C curve. And hopefully you're starting to understand that these are just like level curves. And what was an important quality of oh my gosh. Oh, what's that thing? What's the important quality of the gradient function? It's orthogonal to the level curves. So we're going to talk on this video about how these things are related after this example, okay? Go ahead. Right here, right? Thank you, thank you. It is important. All right, back to blue. Let's pick another value for C. So does C equal 2? Is that going to be easy enough on us? I think it will. So you got 0, 2, 0, negative 2. All right, C equals 2. So that's going to be 4. So good. We'll just put in a 1 for x now, right? Right? 1, 0, and negative 1, 0. All of these points satisfy this equation for C equals what? For C equals 2. That's all we're doing. We're trying to figure out how we choose which points to sub in. And if we choose the right ones, we'll learn more. Okay? Okay, so what does that give you? It's got to be 2, 0. Negative 2. Okay. We'll go black we'll go pink this time. At the point 0, 2, the vector is also 0, 2. Same with down here. Okay? At the point 0, 1, now you can see that these vectors are overlapping. That's why you wouldn't want to graph too many, because they'd all be overlapping. I did, didn't I? Thank you. Okay? So let's see. This is going to be... And now this is starting to look like the paraboloid Remember the paraboloid that we did when we 3D printed it? And we sketched the level curves, and then we sketched the gradient vectors. It's starting to look like that, okay? So that brings us to our final topic of the day, and that would be conservative vector fields. The interruption score right now is Mr. Euland 630, Mr. G 2. So you can interrupt at least 598 more times, and then we'll be back to even. Okay, good. Please interrupt more often. This class is terrible. All right. Okay, a vector field is said to be conservative. Is it frozen?
No, it's timing. It's not that.
Oh, good. If there exists a differentiable function f such that f equals del of f. I got some good mousemanship. The function f is called the potential function. All right, let me try to tie this stuff together, and then maybe you'll start to understand why this feels like we're doing gradients. First of all, conservative vector field. That is stealing a term from physics. Obviously, this math only exists because physics needed it, okay? So, what this means is that a conservative vector field, I hope I don't wreck this, but it means that the sum of the kinetic energy must be equal to the sum of the potential energy. Does that sound right? Is that what it means for a field to be conservative, or for something to be conservative?
At the end and the beginning, there's no. Where do you start with?
The sum of the mechanical energy equals.
Well, mechanical is going to be called kinetic by me.
Well, it's so at one point we're going to that another point. The energy
Okay.
that you have in the system is the same.
Okay. We good with that? So, this is talking the same conservative that your physics teacher talks. But the way that we mathematically prove that it's conservative is that, so this right here, okay, that is our vector field. So if our vector field came as the result of the derivative of a parent function, then it is conservative. So what we're going to say is that the first and easiest conservative vector field that you guys learned is what? No, in here is the gradient vector. This looks exactly like the gradient notation, right? This would be your gradient function. That function is a vector field, because what did the gradient do? It took a function and turned it into vectors by doing partial derivatives with respect to each variable. You remember that? Remember how the gradient of f of x comma y comma z is equal to f sub xi plus f sub yj plus f sub zk. You remember that? And I apologize for my capital F's. I don't truly understand the difference between capital and lowercase f yet, but it probably matters. Okay? It's all right. We're going to do our best on this, and we're going to do better next year. I've already said that. Okay? So, that's pretty much the end of the video. How do we tell if something is conservative, if a vector field is conservative? Well, if we can figure out that it is the result of a derivative of a parent function. So now let's go backwards. You should know this. This is a gradient. You can tell it's a gradient. We've done it before. All the level curves are orthogonal to the vectors. So what's the parent function of this? Anybody? That's right. The parent function, and I can't go more capital than this, so I'm just going lowercase, but someone out there is making fun of me right now. But luckily no one watches these videos. What would our parent function be? X squared plus c plus y squared over 2 plus c. In our next video, we're going to help you find these c's. Okay? Got it? Well, they could be functions of the other variable, and that's what could be tricky. Okay? Can I get a little boom? Boom.